Hello and welcome to a video on equilibrium and reversible reactions. So I'm going to be drawing and illustrating throughout, and I'll be talking you through the parts. So first of all, we'll put our title as equilibrium plus reversible reactions. So first of all, we need to understand what a reversible reaction is. Now the symbol for a reversible reaction is as follows. We have two arrows, one going forwards, one going backwards. This is implying we can go in both directions. Furthermore, the size of the arrow is also important. This is implying the forward reaction is far more present than the backwards reaction, and in this example, the back reaction is far more powerful than the forward reaction. Now, reversible reactions come in all shapes and sizes, but not every reversible reaction is an equilibrium reaction, and that's important to note. So let's go for an example of an equilibrium reaction. I'm going to use A, B, this goes to make C plus D. We'll use this as an example. Now at first you have a lot of A and B and no C and D, because these are reactants and these are our products. And you wouldn't expect to start with products at the start of a reaction. Now as the reaction goes along, our reactants decrease and our products increase, and this is expected, and we might end up seeing a graph that looks a bit like as follows. Our reactants start up high and then tail off, and our products start up low and tail off. And we notice that it is this point here, this is where we reach equilibrium. And this is because the rate of the forward reaction equals rate of backward reaction. And that's what equilibrium is. It is the point at which the forward reaction, going from A and B to C and D, has the same rate as the backward reaction, C and D combined together to go back to A and B. So we have equal parts, equal rate of reaction. We could have different masses or volumes of A and B compared to C and D, but as long as you're making products and reactants at the same rate, you've reached what we call equilibrium. Now, the equilibrium is extremely important because we can manipulate the equilibrium and we can use it in a multitude of ways, and that's what I'm going to be moving on to next. So I'm going to clear the page and then we'll move back. So let's go back to our example. A plus B goes to form C plus D. Now let's say it goes hot in one way, the other way must be cold or cooling. So if you heat it up to make the products, you must cool it back down to make the reactants. And that makes sense, because if you think about it in terms of energy and exothermic, endothermic, they are opposite, but they also have similar energies required. And that's what we're going to link to in just a moment. So, if this is hot and it enjoys a hot temperature, it must be the endothermic pathway. Therefore, this must be the exo. And this is because exo gives out heat. Heat is expelled into the surroundings. And if you have a cold surrounding, you're going to be able to get as much energy out as quickly as possible. If you had a hot surrounding, exothermic wouldn't be able to give the heat out. It wouldn't work very well. On the other side, endo loves heat. It will absorb as much heat as it possibly can. So if you increase the heat of the surroundings, endo will absorb it and it will shimmy over to this side. And that's important later on when we talk about Le Chatelier and how we can manipulate equilibrium, because it allows us to either get more products or more reactants, depending on what we want. And a good example of this is the Haber process. In this process we make nitrogen and hydrogen react together to form ammonia. Now ammonia is the desired product, so we have to manipulate it to make more of this, and I'll go into more detail about this at a later point. Right, let's talk about Le Chatelier's principle. Le Chatelier was a French scientist who manipulated equilibrium reactions to get more product or reactants depending on what was desired at that time. Now, there are several different ones we need to understand. We need to look at pressure, temperature, concentration, and we also need to think about the catalyst in this. So, first of all, I'm going to start with pressure. So, this time we're going to use our example, but I'm going to tweak it slightly. A plus B 2C plus D. Now this number, if you remember from before, two moles of C. We have 1 mole of each of the others, but because of this number in front, it means we've got 2. It's a bit like in maths where you have x or 2x. You don't put 1x in front of it, you just assume the 1. So 2 moles of C. So in pressure, if you increase the pressure, the reaction will shift to side with less moles, plus vice versa. As in, if we decrease the pressure this time, it'll go to the side with more moles. And that's important for us to understand. But we need to explain why this occurs. And the reason is 1 mole equals 24 decimeters cubed of volume. And that's for any gas. Of any gas. So 1 mole of any gas will have 24 decimeters cubed of volume. Now, if we go back to our example up here, we've got 3 moles on the right, and on the left we only have 2 moles, because we've got 1, 2, 2 moles. 1, 2, 3, 3 moles. Now, if we apply this here, 1 mole equals 24 decimeters cubed, but this side will equal 3 times 24, 72 decimeter cubed worth of space. Whereas on the other side, this will equal 48 decimeter cubed worth of volume. Now, this will explain why if we increase the pressure, it will favour this side, because it's got less moles. It takes up less space. And pressure is when you're squeezing it down. You're squeezing the space you have available, so of course it's going to force the reaction over here. So an increase of pressure is going in the back reaction, so I'm going to put that here, increase, and decrease in pressure favours the forward reaction. So if you want more products, you'll decrease the pressure. If you want more reactants, you'll increase the pressure. And that's applicable to any reaction, as long as they are gases and as long as the moles are different on either side. If you have the same number of moles either side, decreasing the increased pressure will have no effect. If they're all liquids or all solids, you can't compress them, so it will have no effect. So it's all down to it has to be gases and different number of moles on each side. Right, now let's move on to temperature. Right, so temperature this time. If we look at this again, and this time I'm going to go back to our original one, not having to look at moles. You do not need to worry about the moles in this one. But this time we need to worry about it being exothermic or endothermic. So we'll say hot, and we'll say cool or cold again. If this one loves it hot, it must be endo, and this one loves it cold, it must be exo. So in terms of temperature, if you want more of the reactants, you'll cool it down. If you want more of the products, you'll heat it up. And that's as simple as temperature gets, okay? But you might be told in an exam, let's say delta H, so that's how energy change equals minus 45 kilojoules per mole. Now this is stating that it is exothermic because it's a negative, so it's exothermic. And therefore, if it's exothermic, we need to cool it down to get to that way. So they might say, oh, the reaction has a minus 45 kilojoules per mole in the backwards reaction. We want to make more reactants, so then you say, right, we need to cool it down to make more reactants. And temperature is as simple as that. Once you know which direction is exothermic and endothermic, you'll know which to do. So endo likes it hot. Exo loves it cold. Exo loves it cold because it wants to give out all that heat. Endo loves it hot because it wants to absorb all that heat. Right, let's move on to concentration. So, with concentration, now this one's quite straightforward. Let's say we increase the concentration of A. What will happen is, as there are more particles, so concentration equals more particles per volume or area. If we've got more particles, and this will link back to our rate of reaction topic, we're going to have far more collisions, therefore more likely more successful collisions. So this equals more collisions. And so therefore, 3 dots equals therefore successful collisions. And if we have far more successful collisions, we're going to have a greater rate of reaction So therefore, we're going to make more products. So if we increase the concentration of A or B, we'll get more C and D. If we increase the concentration of C and D, we'll get more A and B. And this will go until the concentration is dwindled out and we've reached that equilibrium again. Okay? So, concentration, increase A and B, go to C, increase C and D, you go to A. Right, finally, let's talk about catalysts. So the catalysts have no effect on equilibrium. So that means if you add it to an equilibrium mixture, there will be no change in where the equilibrium lies. You're not going to make more products, you're not going to make more reactants. But what you will notice is equilibrium is achieved sooner. And that's because, as we know, catalysts increase our rate of reaction. So of course that means it's going to get to that equilibrium point a lot quicker. So we compare it back to our graph we drew earlier. We had this sort of thing. I know, terrible drawing for this one. Instead of reaching it at this point, we might actually reach it at this point and be sooner along. So catalyst, no effect on equilibrium, it's just we achieve it sooner. So the whole point of equilibrium is that it is a dynamic system. What I mean by dynamic is it can be changed. So, dynamic system can be manipulated, changed. These methods, we can manipulate it to get a desired compound or chemical or element, etc., etc. And what it will do is it will shift to that direction to counteract the change. It shifts to counteract a change. And by change, I mean one of these four things. Well, three. Catalyst doesn't truly affect it. And once the change has occurred, it will counteract it, it will shift until it settles back down. So in the terms of temperature, you increase the heat. Once it absorbs all the heat, if the surroundings has gone back down, you're back to a standard room temperature, back to equilibrium. So that's what it means. If you ever see the word dynamic system, it literally means it can be manipulated and it shifts to counteract a change. And that's why Le Chatelier is a genius. He realized that it shifts to counteract change and he started to play around with these factors. So what I will do is I will put a worksheet up after this video, watch the video, make some notes and have a go at those questions. I'll respond to any questions on it. Thank you.